Hello and welcome to Rocks Lesson 5. This one is about plate tectonics and earthquakes. My name is Mrs. Chiverton and I'm one of the science directors, and I'll be taking you through this next topic. As with all of our other lessons, please make sure you've got either your exercise book or some paper and a pen, pencil and ruler handy in order to make notes and record your information. At the end of this there is the Google quiz to complete. There is an exam question as part of the Google Slides, and there is also several extension activities which hopefully you'll be able to have a little bit of fun with. Okay, so now we're started, just to get your brains working, I want you to think back to some previous lessons and name the layers of the Earth. A little bit of a clue, there are of course 4 layers that you need to be able to name, and for those of you who need an extension, could you tell me what state the rock is in each layer of the Earth? Okay, so hopefully that's got your brains working and you've remembered the 4 layers being the crust, the mantle, the outer core and the inner core. And for those of you who tackled the extension, we know that the crust is a solid, the mantle is the semi-molten part of the planet, the outer crust is liquid, and the inner crust is also a solid. So well done if you got all of those right. So hopefully that's got you thinking and your brain's working, and we are going to move on and look at some new information. So today's learning outcomes, our challenge is to be able to describe what is meant by a tectonic plate and by an earthquake, and to be able to describe the common effects of earthquakes. And our Aspire outcome today is to be able to link tectonic plates with the causes of earthquakes. So this is a cross section of the top part of our planet. Okay, we live on this area, the crust, and in particular this top section. This is the area that we've been able to live and explore, and it's known as the lithosphere, but we can just carry on calling it as the crust. For those of you who like to know what words mean, the lithosphere is made up of hard solid rock, and the litho part of the name actually means rock. Now, that crust is not solid like an eggshell. The surface is actually cracked, and the areas between the cracks are called tectonic plates, and those plates are lighter, so they actually float on the semi-molten mantle beneath. Okay, this is another way that you could record information from this PowerPoint. Today, rather than a big table, I've given you some sentence starters that would clue you in to the key points that you need to get for your notes from this lesson. There is a small table to compare oceanic and continental crusts there. Don't worry about getting all of this information down, because I will keep putting it through on a regular basis at appropriate points in the video. But the things that you need to be aware of: what's a tectonic plate? What's the heat source for the Earth? What do convection currents cause? 4 types of plate boundary. What's an earthquake? What does an earthquake cause? How can we measure earthquakes? And why are earthquakes hard to predict? So, as we've said, the structure of the crust, it's split into many tectonic plates made up of 2 main types, the oceanic and the continental. And on this diagram, you can see the red lines are the boundaries between the different plates. Some of them fall through the middle of the oceans, some of them are across or the edges of land masses. The ones through the middle of the oceans are, logically, oceanic plates. The ones that are through or on the edges of land masses are continental plates. So, when we look at continental versus oceanic crust, although they're both made of solid rock, there are some distinct differences. So the continental crust, as I've said, underlies the continents, the land masses of our planet, and it's approximately 35 kilometres thick on average. Some of it is a little thinner, some of it is a little thicker. It tends to be the older type of crust. Usually most of it is over 1,500 million years old. It's less dense than the other type of crust and can't sink below it. It also doesn't tend to be renewed or destroyed on a regular basis. The oceanic crust underlies the oceans and the seas and is much thinner, approximately 7 kilometres thick on average. It's usually newer than the continental crust. Most is less than 200 million years old. And it's also more dense than the continental crust, and so it can sink below that crust, and it can also be renewed and destroyed. So at this point, I'm going to give you 2 minutes to record the first two parts of our summary. What is a tectonic plate? And what are the differences and the similarities between oceanic and continental crust? Right, hopefully you've got the information down for those first two sections. If you missed anything, you can go back and rewind the video and try and find the information again, but there's also a summary at the end for you to add to your notes if you need to. So this again is a diagram of the main tectonic plates, and those plates are moving around. They're moving closer to and further away from each other at varying times through their history.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
So, when we look deep inside the Earth is remarkably still cooling, even though it was formed 4.5 billion years ago. And deep within the core, there's radioactive decay of rocks, and that is what keeps our planet hot. The hot core sends that heat up into the mantle, you saw that in the video, and this is the source of the heat driving the convection currents in the semi-molten mantle. The convection currents carry heat from that hot inner mantle to the cooler outer mantle, and those convection currents beneath the plates move the tectonic plates in different directions. You could demonstrate this with a pan of water and some little wooden blocks over the top of it. If you start heating the water as the convection currents develop in the water, then it will actually move those little wooden blocks around. And this is like a model of plates on top of the mantle, with the hot core being the stove effectively at the bottom of your model. So when we look at this, underneath the tectonic plate, the heat from the core drives rising currents. So we get that movement of things that are hot rising. When they get away from that heat source, they then cool down and they start to sink, but then of course they come in contact with the hot source again, and we get this continual cycling, and this is what's known as a convection current. Now, underneath the solid tectonic plate, this will just be a continuous process. However, when there are plate boundaries above one of these areas, we have the same process where convection currents develop as a result of hot things rising. But as those convection currents move, they will move boundaries away from each other in some areas, and then in other areas they may move them towards each other. And we can get all sorts of things happening at this point. We can get something called subduction zones, we get friction-induced movements of the plates, and we get splitting and spreading. All of those we're going to look at in detail. So you hopefully now know what the source of heat for the Earth is, and also what happens when convection currents occur in the mantle. I'll give you a minute just to record that information. Okay. So tectonic plates are moving very slowly, only about 2 to 5 centimetres a year. The plate boundaries are where two plates meet, and we need to be aware of 4 major types of plate boundaries: constructive or divergent, destructive, collision or convergent, and conservative or transformation. We're going to go through each one of these separately. So constructive margins, our example here is the mid-Atlantic ridge. Okay. So this is where two plates are moving away from each other. They are both oceanic crust, and as the plates move apart, what happens is that new rock is actually formed. This is known as seafloor spreading. And you can also see the mid-Atlantic ridge running through the centre of the country Iceland. So at constructive plate boundaries, this is where new oceanic crust is being made. That's why the oceanic crust is often younger than the continental crust. It's convection currents moving those plates apart and causing magma to well up from the mantle. It erupts as lava on the surface to fill in the gap between the two plates that's formed by them moving apart. And then it cools and forms new basalt type oceanic crust. New plate area is formed. And as a result, the Earth's surface area increases due to the formation of that new crust. And this process is known as seafloor spreading. So a second type of boundary is a destructive margin, and an example of this is the Andes in South America. Where you have destructive margins, we have two plates moving towards each other. We have an oceanic plate and a continental plate. Now, what we end up forming is a subduction zone, and that's when the denser oceanic plate is forced to sink below the continental crust as they move together. This is an aerial view of the Andes, and a reminder that the thicker, denser oceanic plate, seen on the left, is moving underneath the continental plate, seen on the right, and this is called a subduction zone. When that plate gets forced down, it reaches the hot mantle. The rock is a very different density and tries to force its way back up to the surface, and it often erupts through a weak point in the crust, building a volcano. We get the folding of the continental plate as the two plates are forced together, and this forms the characteristic shape of the mountains in the Andes. And often where those plates are sliding past each other, friction stores energy in the rocks, and when that energy is released in a jerky movement, we get earthquakes, but more about those later. So another area where plates are meeting, moving towards each other, is a convergent plate margin, for example, where both the Alps and the Himalaya mountains are formed. In this case, what you are having are two continental crusts moving towards each other, and we end up with something called a collision zone where those two meet. And as a result, we end up with mountain ranges, which are constantly growing. So plates are at parts of the Earth moving towards each other. When continental plates collide head-on with other continental plates, the result is a process called upheaval. And this is partly because the two types of crust are the same density, so therefore one cannot be subducted, one won't be forced down below the other one. That gradual forward movement of each place will create extreme pressures, and that builds up over time. And as the rocks are forced together, they're pushed up. The rock strata become folded and they rise to create mountain ranges. And these ranges, like the Himalayas, continue to grow on a yearly basis. So the final type of plate boundary that we need to be concerned about are the conservative or transformation boundaries, such as the San Andreas Fault that runs down the west coast of North America. In this situation, we have something called a fault line. That fault is where two plates are trying to pass by each other in opposite directions, so they are sliding past each other. So that fracture line between the two faults tends to have very rough surfaces as their plates are trying to move past each other. As you know, where you move two rough surfaces together, it creates the force of friction. And this is creating large strains along those faults as the plates slide horizontally past each other. This results in pressure building up in the rocks on both sides of the fault. And eventually that pressure will build up enough that the energy is released in sudden jerky movements, and that's what we would describe as an earthquake. And this area all down the coast of America, down through California, and particular areas like San Francisco and Los Angeles are very, very prone to earthquakes along that fault line. So at this point, you should have enough information to fill in about the four different types of plate boundaries, what they are and what happens as a result of those movements of the plates around those boundary lines. I'm going to give you 2 minutes to complete that information. But again, if you need to pause and re-watch any of the videos, you can do that at any time in order to fill that in, and there is a summary at the end. Okay. So I want to now look at that connection between volcanoes and earthquake activities and the tectonic plates. So the current map shows some of the main tectonic plates that we know around our planet, with the black lines being those boundaries between those plates. If we overlay onto that where most of the volcanic and earthquake activity occurs, you can see that in many cases there is a pattern between where that volcanic activity occurs and those plate lines. So now we're going to look at a little bit more detail at earthquakes. So earthquakes are mainly caused by tectonic plate movement, but it can also be caused by volcanoes and meteor impacts as well. Earthquakes are vibrations that travel through the earth as something called seismic waves. They cause shaking or trembling of the ground caused by the sudden release of energy as plates move past each other. And the continuing adjustment of position can result in aftershocks. Now you'll do more about seismic waves when you move on to physics in year 10 and 11. But would you believe there are about 8,000 earthquakes a day around the world? Most are very minor and often in uninhabited areas. So the impact of earthquakes. It obviously depends on the strength of the earthquake as to what the impacts actually are. Having experienced an earthquake many years ago, which resulted simply in pans rattling and furniture shaking a little bit, but no major damage, they can be quite minor events. But of course, more extreme earthquakes can have much more extreme effects. So for example, extreme earthquakes can actually cause whole buildings to collapse. And buildings now built in earthquake areas tend to have a different design in order to allow them to withstand more minor quakes, but even they will struggle with more serious ones. There are often fires in conjunction with earthquakes. Now this is often as a result of fracturing of gas mains and electrical supplies actually causing outbreaks of fire rather than anything to do with magma or lava. There's often damage to transport systems. Now that could be freeways like this one where the bridges and the supports have collapsed, or it could be, as in the case of this train line, where the movement of the earth has actually bent and distorted the tracks, leaving the earth in a permanently different position. They can, as has happened in the last 20 years or so, cause very serious tsunamis, tidal waves, where great waves of water travelling at huge force engulf lands around the coast. And they can result in ground failure. So you can actually get areas where there are huge cracks and areas where the earth has been completely disrupted. So they can be quite serious impacts, but as I've said, it very much depends on the strength of the earthquake. So at this point, you should be able to explain what an earthquake is and what effects that earthquakes can have. And I'm going to give you 2 minutes to complete that information. Right, hopefully you've got all that information down. We're now going to look very briefly at the detection of earthquakes. So, there is a piece of equipment called a seismograph, and that is used to actually measure the waves of energy passing through the planet. We can also use laser beams. Now they're used to detect horizontal fault movements. So places like the San Andreas Fault, they actually have laser beams set up with a reflector, and they can see if that beam gets disrupted, it means that there's been movement. We can also use GPS monitors, so that's using satellites in space to look at the movement of the Earth's crust, both in horizontal and in a vertical movement. And finally, we can use things called tilt meters. Now, these look a little bit like the kind of spirit level that you would use in construction as a carpenter and so on. And again, as the Earth moves, if it rises or falls, the liquid will flow from one bulb to another, and you will be able to measure the amount of tilting. So all of those are pieces of equipment that scientists will use to monitor earthquakes in areas where they think that earthquakes are likely to happen. And it's very useful for scientists to be able to identify both the focus, so where the actual fault happened, and also the epicenter, the point above the focus on the surface. That will give them information to be able to predict how much damage is likely to occur and who is most likely to be affected by a quake happening. Now, there are various measures for working out the size of an earthquake. The two main scales that we know about are the Richter scale and the Mercalli scale. And I'd like you to have a think as I talk about them as to which one you think is probably most useful to people. Now, scientists tend to talk about the Richter scale. It measures the magnitude of how powerful a tremor is, and this is used in a seismograph. It's measuring the amount of energy that's actually been released as a result of the quake. It's a logarithmic scale from 1 to 10, and it means that a size 6 on the Richter scale is 10 times more powerful than a size 5 earthquake and 100 times more powerful than a size 4 earthquake. The Mercalli scale concentrates on how much damage is caused by an earthquake and is based on observations that could be made. There's been various versions of the Mercalli scale. The original one worked on a scale from between 1 and 12, and the more recent one goes from 1 to 10. It looks at how much shaking of the ground would actually occur, and then as a result there's a description of the likely amount of damage that would also occur. So we have 1 where the shaking is not actually physically felt and we would have no damage whatsoever, to 10 of extreme shaking, resulting in some well-built wooden structures being destroyed, masonry and frame structures destroyed with foundations, and rails bent. So that might have been similar to the picture I showed you earlier about the railway, where they'd actually bent the lines there. So there are earthquake prediction programs because in certain areas of the world, earthquakes can cause a lot of damage and a lot of inconvenience for people. These prediction programs will include laboratory and fieldwork studies of rocks before, during and after earthquakes to look at patterns. They will monitor activity along major fault lines using some of the monitoring equipment we talked about earlier. And they will produce risk assessments looking at the possibilities of what will happen in certain areas. However, it is incredibly difficult to predict earthquakes and tsunamis, and that's because we can't actually see what's going on deep within the earth. It's impossible to measure the forces here deep within the earth. Again, we simply don't have the scientific equipment possible at present. And we don't know what the forces actually needed to cause earthquakes are. And finally, those movements are often very sudden and jerky, so it's very difficult to predict when they're actually going to happen. So we can only make what's called informed guesses. And sometimes there are strange things such as animals that can actually be quite helpful in predicting that. And I don't mean that your dog listening to your seismograph, but often things like insects and birds changing in behaviour can be a clear indication that something like an earthquake or tsunami is about to happen. So that should allow you to fill in the final two sections of our summary. How do we measure earthquakes and why are they hard to predict? And I'm going to give you about a minute to complete that. Okay, so this is a summary of all the information you should have been able to gain from the video. You can pause the video at this point and use this to check off the work that you've made in your notes and add any additional information. Once you've done that, you should have all the information you need in order to complete the Google quiz. This is just a summary of the table comparing the oceanic and continental crusts as well. And again, you can pause the video and check your information off. So, task 1 now is to complete your actual Google quiz. Make sure you have your notes at hand so that can help you when you're completing the quiz. Task 2 is also on the Google Sheet. What it's asking you to do is describe how tectonic plates move. It's telling you which keywords you should be able to include in that: tectonic plate, mantle, convection current, heat, float and crust, but add any other extra words. And you could be given credit for an accurately drawn or annotated diagram. Take a photograph of it and upload it for your teacher to see. And you're looking at about 4 marks on the exam paper. Task 3 is just more a little bit of fun. Okay, so in this experiment, you're going to need a paper plate or some other similar container, some shaving foam, please ask permission before you use it, some red food colouring, but this is optional, just to make the shaving foam look a little bit more like lava, and some square biscuits or crackers, doesn't matter which you use. You'll need a beak of water and something to stir with, that could be a spoon. If you work through the instructions, you put your shaving foam into your dish, add a few drops of red or orange food colouring and stir to make it look a little bit like the fiery orange mantle. Place the 2 crackers on top, and that represents the cooler rigid crust. And where those 2 crackers meet, that's our plate boundary. So we have set up our model of the Earth. To represent constructive boundaries, what you need to do is to press gently down on each cracker whilst also pulling them apart, and watch what happens to your magma. And that should represent the lava bubbling up between the plates, and it would solidify if you leave it long enough, just like the rocks that they would form. A transformation boundary is where the 2 plates are grinding past each other. So in this case, you need to push the crackers gently together so that their edges are touching, and then try and slide them past each other. They should grate a bit, but eventually you should be able to get them to move. A destructive boundary is where one of the plates is subducted below the other. So press one cracker biscuit down underneath the other one, forcing them together, and you should see that one will rise up and start effectively to form your mountain there. And then the final one, this is where the water comes in. You'll need to dip the end of each of the biscuits or crackers into some of the water so that the edges of them go quite soggy. All right, you could do it in tea if you wanted to, but water works best. Then place the 2 soggy sides together and gently push them up. And what you should see is that those biscuits will fold on each side and gradually form mountains, just like the Himalayas. So hopefully you can have some fun modelling our different types of plate boundaries. This is an alternative that you can do as well. So Jello is just jelly, which you need to make up following the instructions on the tin. I'll leave it secure somewhere so it's solid. And then the idea is for you to try out different designs to see which is the best at surviving when an earthquake is happening. If you don't have marshmallows, you could use something like blue tack, would work just as well. Or plasticine or Play-Doh perhaps. And the idea is to try several different designs to see which is the most effective at withstanding an earthquake. Try to control your other variables by using the same amount of materials and try to keep the shaping the same. Thank you for listening today, and I hope you enjoy your attempts at building some earthquake-proof buildings.